Okay, so good afternoon, everyone. I'm Luiz. I'm a second-year PhD student at SLU, Umeå, Sweden. And today I will be making a joint presentation with Langning. I will present about my current PhD work, and she will close with an overview of the work we've been doing on bark beetles. And we have recently finished the manuscript on several data sets across Europe. And this will be also a RESDiNET paper, and I should present this, which also includes the data that I will present now. And my work is linking hyperspectral remote sensing with sapflow data, where we detected some instances of hydraulic failure, and I'll show how this can be detected from airborne platforms. And this work is in partnership with Jose Lopez, which is a researcher in the Forest Ecology and Management Department. And just a quick overview on the previous work we've been doing with drone images. First of all, this research framework on bark beetles in our group, we started when we had the outbreaks in 2018 and 19, where Langning started to work with this topic, and we first started with satellite images. And that's when we saw there are so many limitations. We have so much noise, so many different trees in one single pixel, and then that's when we thought we need to look at the individual tree to see what exactly is happening to these trees. And the first study that we had was with a multispectral drone. It was an experiment conducted in 2021. And then in this specific setting, we had 3 red edge bands, which is already much more than most commercial multispectral systems. But we still miss some spectral information for some regions that might be relevant for detection. And then from this paper, the authors, they developed this new multiracial indices based on these red edge bands that significantly improved the detection rates of infested trees from previous studies. And this is very highly correlated to the chlorophyll content of the needles. And this, let's say, is the overall standard when it comes to forest health, that most studies find the red edge related features as the most sensitive to forest health, and mainly because of the correlation to the degradation of chlorophyll when a tree is damaged. But on the other hand, there's this recent study that was published last year from hyperspectral data collection in Finland that was developed by Langning and some partners in FGI. In this instance, then they use hyperspectral images. So then there were hundreds of bands and information from all of the spectrum. And from this paper, they derived this new wind-shoulder curvature ratio indices. And then some of them are produced from derivative curves, and some of them are produced from individual bands that then they could, in theory, be transferred into multispectral systems. And this is even further improved how trees could be detected. And on the opposite of what has been done in the past, these are indices that are more related to the carotenoid contents of the needles. But there are some limitations here from the study that needs to be further tested, because the data was collected during the second swarming of the bark beetle and only applies to one single site in Finland and one single year. And then we'd like to validate this also with further experiments. And another key factor is like an overall deficiency on all of these pre-emergence studies. There is a lack of understanding of what is happening to the targets that we are measuring. So there is some information in the literature that we usually are basing on, and there is just this general understanding that the tree is losing the vitality in a smooth and continuous process, and we usually are detecting them in different weeks. So we assume that every single week the tree is getting more and more damaged until it dies. But none of these previous studies that are using remote sensing at the individual tree level, they have any measurements on the physiological traits of the trees to understand what's really happening to the objects that we are studying. And this is what we also try to fill this gap with this study, to see what's changing, how much is changing, and when it changes, and how this is related to the spectrometrics. And also, especially because when you think about bark beetles and we are doing airborne monitoring, the responses that we are getting are indirect, because then the beetle is in the bark, right? So there has to be a chain of effect to affect the canopy. You need to further understand this to understand how this is affecting the reflectance. And then the data I'll present today is from this experiment that was conducted in 2023, also in Enstorp, the same area that Alice just presented. And then there we had four stands. In each of these stands, we had 6 field plots with 15-meter radius. And in this whole experiment, we monitored a bit more than 1,000 trees. And then we had a pheromone bag in the center of each plot to stimulate the infestation in those sites. And then we had 3 different types of data collected during that year. So we have a field inventory. So every week, we have an assistant going to the field, and for all the trees, collecting the information on bark beetle infestation. So you know exactly when this tree was attacked, what was attacked. And then simultaneously, we have 7 campaigns of hyperspectral images with 2 different cameras. One of them is the visible near infrared camera, and the other the SVIR camera. So we had 7 flights during 2023 during the growing season. And what's very new in the study is sapflow monitoring. And then we had 2 plots in 2 different stands where we mounted the sapflow stations, and each of the stations can measure the sapflow of 8 trees. So in total, we have 16 trees that were monitored during that year, and data was logged every 15 minutes. And this is to show the setup of the sapflow monitoring and how we evaluated the spectral response. So this is how the station looks like, and the station has cables connected to 8 trees. And then this is the sensor. And then from this sensor, we estimated a variable called sap flux density, which is an estimate of the amount of water that is being transported by a cross-section of the tree per hour. And then we use this sapflow data to assess what's actually happening to the tree, how the hydrological response happens after they are colonized by bark beetles. And then these are the 2 plots. So we have one plot here that we had from the 8 trees, we had 3 trees that were infested by bark beetles. And on the other plot, we had 2 trees. So in total, 5 of the 16 trees were infested by bark beetles. And to see how the spectral response was happening after the colonization, we calculated 32 vegetation indices, both from derivative curves or from single bands. And then we assessed when a tree was detected based on when the value that this tree showed was outside the value of the healthy trees. So then we know that the damage is causing a deviation on the spectral information for this tree. So this is an example for one of the plots and showing several indices across time. And see, for example, some of them are very bad at recognizing damage because most of the infested trees have values that are merged with the healthy trees across time. And some of them showing like a very strong difference. And then we say that in this case, this tree could be detected. And then we also tested, besides using the original value of the VIs, we also tested if we calculate the changes that these values have from the first weeks of the data collection, if this could also improve the detection, because then we are seeing how much of the spectral change occurred. And for this, we calculated these normalized indices. So pretty much we take the value from a week and we see how much is the relative change to the value of the first week. And for the first week, you also tested different weeks to see if there was an effect. And at first, the first campaigns were flown in different weeks because of equipment problem. But then we tested, for example, for the effect standard devenir, week 16, 18, and 23. And for the indices that come from the SVIR camera, week 20, 22, and 24. And these are already the results, like an overview from all of the trees of the hydraulic responses. This is a sapflow curves. And then for the healthy trees, we observed that everything was normal as expected. So we have the daily cycles of sap flux density fluctuating up and down. And that was expected. And then for the infested trees, what we saw by our surprise is that most of our trees presented the full hydraulic failure between 3 and 7 weeks. So the water transportation did not only decrease, but it fully stopped with no further recovery. And then from this, we identified 3 different cases, and I will explain what these cases are and how the VIs respond to it. So the first 3, this is an infested tree that it actually didn't show any response in 2023. What we saw was that the sapflow sensor was still mounted in the next year, and then only in April the hydraulic failure happened. But in this case, this tree was still pretty damaged from the bark by the end of the season, but the crown was still green. And in this case, when the hydraulic failure occurred, we could detect it only by week 30. And here I have a selection of VIs. So this is like the green shoulder indices developed by Langning. Then you have the PRI, which is a more or less a plausible comparison because it uses similar wavelengths. And this is a red edge indices related to chlorophyll and the severe index related to LAI, to water content. And we see that only the green shoulder allows us to detect these three in the same year. But still, if we think about pre-emergence detection, this was still not possible because in our sites, the bark beetles, the fetal generation emerged in week 28. So then we have 2 weeks left to detect this tree. And then the second tree was the most extreme case that we saw, which is a tree that had the hydraulic failure very early during the growing season. So around week 22, we already saw this hydraulic failure, which is surprisingly fast. And in this case, we see, because it's a very extreme case, we see that many of the indices, they respond, and we can detect this tree in week 26. So that's 2 weeks before the emergence of the bark beetle. So that's a good case of pre-emergence detection possible. And then for the other 3 trees, we had a bit of a different case, that the hydraulic failure occurred a bit later during the growing season. And it occurred actually 2 weeks before the emergence of the bark beetle new generation. So in this case, we only detected these trees 2 weeks later during the emergence week. So the pre-emergence detection was not possible. But then in the same way, this green shoulder indices was still very efficient in capturing these changes, while the other indices only responded later in the year. And then from this, we derive these 2 different cases that we can identify. So if we have these cases of moderate damage scenario where we have the hydraulic failure happening very late in the season, then we can detect these trees not in enough time for interventions. But then when we have a severe damage scenario where we have this hydraulic failure happening much, much earlier in the year, then that's the situation where airborne monitoring can be enough for timely interventions. Yeah. But then we're looking at the data this week, and we realized that this actually might change a bit the conclusions for these results, because these sapflow sensors, they have 3 needles that go into the bark, and the sensor is located in different lengths in this needle. And this data that I'm showing now is of the outer layer. So you see that this hydraulic failure is actually what we are seeing in the outer layer. But then when we went to see the other layers, we see that there's still actually some sap flow happening in the inner layers. So the fungi, it still hasn't blocked the sap flow in that case. So I would say there are 2 implications from this, changing the conclusions. One is that the trees are actually dying later than we expected. So when this starts, we can already imagine that the tree has some damage occurring, but the full mortality of the tree is actually happening a bit later. So not so good for management, for timely interventions, because then we see that the tree is actually dying later. But from the remote sensing perspective, then we see that this index is actually capturing this change only 1 week after the hydraulic failure occurs and the tree collapses. And this is also very important because, as I said in the beginning, most studies before that are doing this kind of time series detection, they kind of assume that the mortality is like this, right? But then what we see is that actually in the beginning, the tree is functioning normally. And the only thing that's happening is that the beetle is feeding on the phloem. And then you start to have effects on the root, but that's a very delayed effect if you think about damage that can be captured from the canopy. So the tree, what we see is that the tree are actually dying from hydraulic failure. So everything is normal, and then the tree collapses. And then we start a few days later to be able to see these effects from the canopy. And then this was from the plots that we had the sapflow sensors, but then we started to want to map this hydraulic failure across the rest of the experiment. And then, as Alice already mentioned in her presentation, this is the data from 2023, where we had the endemic year. So the bark beetle population was very low. And a lot of the plots in our experiments didn't get attacked at all, only in the tree with the sapflow or with the pheromone bag, or only 1 or 2 trees. So this analysis, which we restricted only to the trees that had at least 5 infested trees. So it's closer to an outbreak scenario. So here in this analysis, I'm considering 227 healthy and 56 infested trees from 7 plots. And again, I'm calculating the detection rates as the proportion of infected trees that have VI values outside the range of the healthy trees. And these are the original VI values as calculated from the formula, and it's considering the change from the start of the season. And then what we see is that we have some red edge indices here, like this, from the multi-ration index to the NVDI. So they are improving when you consider the changes from the beginning of the season, because also their signal is affected by a lot of other things beyond damage and stress, but also by chlorophyll content and LAI, which is changing during the season. So we have some improvement in the detection curves of these indices, but the detection rates are still inferior to the green shoulder indices. And the green shoulder indices are still performing more better than PRI. That is the current benchmark for this green region of the spectrum. And then what we also see that is very interesting is that the green shoulder ratio 1, which is based on derivative curves that you can only obtain from hyperspectral data, it doesn't necessarily perform better than the simplified version, which is using just a few bands. So this means that we could possibly adapt this for using in simpler multispectral sensors that can actually be used for operational uses, because the hyperspectral camera is like a very chunky equipment that can fly only 10 minutes. So in this case, it's not very practical. But then with this index, the simplified version, we could actually try to obtain like operational monitoring. And we also could expect that these trees, like this index is detecting 1/3 of the trees by week 26, which we then assume that are the trees with early hydraulic failure, with the severe damage scenario, detecting 2/3 of the trees by week 28. So these trees with late hydraulic failure, and then we cannot detect, not because of the remote sensing technology, but because of the physiological constraints, because nothing much is happening to the trees up to that point. And why this index is so good at capturing the stress is related to the carotenoid contents, which is a group of pigments that have a role in photoprotection and protecting the trees from harmful radiation, especially under stress scenarios. And then this can be a very good indicator of early vitality decline compared to other indices that are related to the chlorophyll. And then the chlorophyll will only start the degradation much later. And this is in this Eiger's paper, which you are interested to read, that they're showing how they are have a strong linear correlation between the green shoulder indices and the carotenoids. And this is a bit of a breakthrough for our group, because so far, if you look at what we have been doing, we are always comparing the VI values of infested trees with healthy trees. So it's like an analytical procedure for us to have a way to measure very clearly which VIs are better or not. But if you think about operational use, this is still very limited, because you always have to have a control of healthy trees, right? And then if you look at a regular drone image, for example, this is one of our field plots that we have here, our infested trees in the center and healthy trees around. In the regular true color image, we cannot see any differences, right? But then when we change one of the visible bands by one of the green shoulder bands, let's see if it will work. Yeah. Then you start to see very clearly when we have abnormal spectral anomalies here. And then you can even see at the branch level which part of the tree is attacked, is actually affected. And then in this case, we can say that this index is so stable for healthy trees that we're actually able to visualize it just by adding us in replacing it for one of the visible bands. And of course, this visualization can be done with any other spectral metric, but the problem is if you use some other metrics that are related to chlorophyll, for example, then you start to have a lot of false alarms. Then you see here, for example, I hope you can see that. You can see this very strong pink color in some trees that are healthy, are not infested by bark beetles. And this happens for all of the red edge indices, and it's also a problem for PRI, for example. And in the case of the green shoulder indices, these false alarms help much less. And we're actually seeing exactly which part of the tree is affected by the hydraulic failure. Yeah. Now let me continue.
Thank you. So we have another study that we try to do a cross-European assessment on the early detection, because so far every group collect their own data and have their own way of processing images and choose their own best vegetation indices and have their own way to compare the healthy group and the attack group. And that means it's super difficult to compare between different sites, and different sites also have different outbreak scenarios. So our idea is here that we want to make a benchmark. So we have data from different study area across Europe, and then we standardize all the precise chain and see if it's possible to compare and answer the important research question: how early the infestation can be detected. So this is our data set. So from 4 different countries, and then of course in some countries there are even more areas that are analyzed in the data set. And we have a case from Sweden, from Finland, and also from Central Europe in the Alps area and in the Czech. And so to summarize it, we have data from 12 areas, and then including 6 different dragonfly campaigns with time series, multispectral, hyperspectral images, and then covering thousands of infested trees and more than 13,000 healthy trees. And one important information to consider is the thermal sum, and we also list it here. So in this case, it's a bit surprising because the data from Finland and from Sweden were actually having higher degree days than our data collected in the Alps area and in Czech Republic. And that's because in the Central Europe, we have data from mountainous area, so higher elevation. So the thermal sum is actually lower than Nordic country. So if we jump directly to the conclusions, first we harmonize which type of sensor are used, or even giving a suggestion which type of sensor should be used. So we have Maya S2 sensor that's having 3 different red edge bands. We call it red edge 1, 2, 3. And then in MicroSense, it choose only one red edge band, that's red edge 1. And then the DJI series drones, they choose red edge 2. And then we explore if that's make a lot of difference. And because our sensor from Maya have 3 different bands, including this red edge 1, 2, and then it's possible to compare the detection rates. So we can see in this case, the purple one is from the red edge 2, and that's the DJI series, and also the same. So by comparing these 2 different red edge bands, we see that the red edge bands in the DJI series is not sensitive for the early stress at all. So we recommend we use Maya S2 or the MicroSense because they have this sensitive red edge, and red edge 1 is the most sensitive one. And the benefits, if we must compare the Maya S2 and MicroSense, they are actually very similar. So having 3 red edge bands is slightly better than only having 1 sensitive band in the red edge. And we also compare how much difference can be made between the multispectral sensor and the hyperspectral sensor. So these are the curves that shows the most difference. And the green one is actually from the green sugar indices. And then we see that it can detect about 2 or 3 times more infestation compared to using the red edge bands. And that's the case also for the data we first published in the Finnish data. And then the second analysis in the Swedish dataset. And also we did a comparison in the Czech Republic. And this also showing why we choose the shoulder bands. Because in this data set, the infestation actually happened in the week 23. And then the red eye, the shoulder one is the best one against the false positive. So it doesn't detect trees before the natural attacks. And only the outliers among the weeks when the Jones was flying too early in the day. So really low sun levels. And that's the outlier that is the bummer. Otherwise, the really always a good place for with the development of infestation. And another perspective we compare between the 2 sensors is the bandness. So assuming that if we don't consider green shoulder bands, we only consider the red edge bands calculated from the multispectral sensor or hyperspectral sensor. They are actually very similar. So we conclude that the hyperspectral sensor can detect more trees, not because they have narrow bands, but just because they have this green shoulder region. So we assume that if a multispectral sensor can also provide this green shoulder bands, then the multispectral sensor can also be really good detector for the stress tree. And most thing we want to highlight here is that this tree decline rate is extremely local. So these are the case when we calculate the average, and we see the middle weight 25, that's the most critical time for early detection. After your averaging, it's about 10% detection rates. So we kind of draw the conclusion that early detection is not possible if you average. When we start to look at individual patches, so we see that they have a lot of variation. So in some of the infestations patches, we can detect even 40 and 60% of trees in a very early week. And that's also the case almost among all the area that's involving several patches that are unmatched. For example, in the Alps, they analyze average 1,000 of trees, the detection rate is really low. And we were saying that it's not possible for early detection. But actually, if we go into the small patches, we can see that detection rate is even higher than 90%. So that's also one more conclusion, the detection rate is extremely low. So even the plots within the same stand and neighboring each other, the detection rates can be so different in each other. And also we see a faster decline in this output year, but at the same time, there's more similar range between different countries. And this is sum up. So this line is the average beginning of the attacks, and this is in the middle of the attacks and development of the larvae, and then this is the average for the emergence. So we aim to detect all the trees before this line, and preferably before this line, so we don't have enough time for the damage control. And we also adjust the standard because if we aim at detecting the patches, we don't actually need to detect every tree to make action. Let's say if we can detect half of the infestation with a patch, that's already enough to draw attention to say the forest manager needs to go to this area and check and do the damage control. So we define that as like 50% of the detection rate is enough to help the forester find the patch. And according to this standard, about half of our data set shows that they can be the infestation patches can be detected before boarding images. So half of them achieve the early detection before the next generation. And then also 25% of them will achieve early detection 1 month before the next generation comes. So that's showing how the remote sensing data can help for the damage control. And in the other perspective, when we harmonize the detection method, like what we show here, so all the data are using similar way of presenting data using the same weights and indices, and we show how the trees decline through time. And then this is another tool we can use to analyze in some area the tree declines so fast, and another patches the tree declines so slow. So we can explore more or try to explain why this happens. So far we have population data. We compare between countries, and we don't really see significant difference. So we draw the conclusion that we assume the attack density is the driven factor why the sum of the tree declines so fast. But this is still ongoing work that require more analysis on the extremely local level. So that means we will need high resolution remote sensing data, high resolution environmental data. And then also highlighting that when we average it in the landscape level, a lot of information may be getting averaged out. We don't really see the variation between the sets. Yes.